Hi everybody! Today I'm going to show you everything that I learned while creating a basic chess engine in Python. Let's begin by going through the Minimax algorithm, which is how the chess engine decides its moves. Let's explain this using an example. In Minimax, there are going to be two players, and one of them is going to be trying to get the highest score possible, while the other one will be trying to get the lowest score possible. In this example, blue is trying to get the higher score, while red is trying to get the lower score. And in this example, it might be easier to think about it from the bottom up. So let's look for the current blue node. It has a choice of either 8 or 23, so it'll choose the move with the higher score of 23. Similarly here, blue has a choice of either -12 or 27, so it'll choose the higher score of 27. This time, it's red's turn to pick, so they have a choice between 23 and 27, so they're going to choose the lower score of 23. It should start to be making a bit more sense now, so let's just go through the example a bit quicker. Next, let's talk about how we assign a score to each board evaluation. Starting with the pieces themselves, we'll assign a certain value to each piece, like a pawn being worth 1 point, while a queen is worth 9 points. In addition, we'll also be using what is known as piece square tables, which gives us a rough idea of how valuable a piece is worth based on which square it's on. In this example, knights are penalized for being near the edge of the board because they have less squares that they can move to. On the other hand, they're rewarded for being near the center of the board because that means they control more squares and they have more options available to them. And then, to get the score of the current board, we'll just sum up the value of every single piece on the board and return that. Minimax is a good algorithm for finding the best moves in games, but it's very inefficient due to the way it calculates the best moves. As the search depth increases in a game of chess, the number of positions also increase exponentially, which results in very long waiting times. Luckily, there's another algorithm called alpha-beta pruning, which allows us to skip unnecessary branches of the search tree. Using two values alpha and beta, we can track the best move that the maximizing player can guarantee, and we can use beta to track the best score that the minimizing player can guarantee. Using these values, we know that if beta is ever less than or equal to alpha, we can safely skip or prune that branch from the tree because we know that it will not affect the final decision. Let's take a look at the difference between alpha-beta pruning and normal minimax using the example from before. We've reached a scenario where beta is less than or equal to alpha, but there's no more moves left in this move branch, so we'll continue on as normal. Once again, we've reached a point where beta is less than or equal to alpha. We saw earlier in the search that blue already has a choice of choosing 23, And in this move branch, we notice that red, who is the minimizing player, has a score of -9 available. We know that due to the rules of Minimax, red will never choose a value that is greater than -9. This means we can safely prune the remaining moves from this move branch because we know that blue will always choose the left branch since it has a higher score available. Using the profiler, I was able to locate the bottleneck for the program, which is the move generation and simulation. Since the Minimax algorithm evaluates multiple future positions, altering the actual board during simulations would corrupt the game state and lead to potentially incorrect evaluations. To get around this problem, we're currently creating a brand new independent copy of the board for every single move before we simulate it in order to prevent modifications to the original board state. Unfortunately, creating a deep copy of the board is an expensive operation, and doing that for every single move adds up over time, making the program extremely slow. A good way to work around this problem is to create a move stack, where after every move we simulate, we'll add that move to the stack, and once we reach the end of a move branch, we'll recursively undo the move until we reach the original board state. Earlier, we saw that alpha-beta pruning made our Minimax algorithm about 3 to 4 times faster, and it was pruning around 25 to 50% of the search tree at a depth of 3. But what if there was a way to find the lowest B values and the highest A values even faster? That would mean we could prune even more branches from the search tree. But how can we do that? Currently, moves in the search trees are evaluated in no particular order, and in this example, we were only able to prune 2 nodes from this huge tree, meaning we still needed to explore most of it. But what if there was a better ordering of which we evaluated the tree? Since it's White's turn, why don't we sort the values from highest to lowest? By properly sorting the moves from the highest to lowest score, we were able to prune 3 times more nodes than before. Also note that in chess, each move branch is going to have significantly more nodes in it, making alpha-beta pruning even more impactful. There are plenty of good options for sorting heuristics in chess, but for now, let's just use one of the more popular ones, which is MVVLVA, or the most valuable victim, least valuable attacker. The idea of this heuristic is to find the moves that'll capture the opponent's most valuable piece with our least valuable piece. For example, taking your opponent's queen with your pawn is more likely to be a better move than taking it with a rook or your own queen. After all our improvements, let's see what AI has to say about our program. There's still plenty more options out there for speeding up the engine even more, but I don't understand this well enough to explain them yet.